these suppressions at this power level was similar, but I'm saying there's a lot of optimization that needs to occur. Now, in this particular chart, in order to show you that typical efficiency in a radio head doesn't depend on the amplifier alone. In this particular chart, it's a 2TX, 2RX MIMO radio head. The drivers consume 8 watts. The PA output is around 20 watts per side. And let's assume that the final stage efficiency is 50%. Here I have dissipation for a linearization path of around 12 watts, which is pretty normal. I don't think you're going to be able to, unless somebody has better experience, have a linearization per path of much less than 12 watts. So you'll see that the radio head efficiency turns out to be around 22.3%. If I were to increase the final PA stage efficiency to around 60%, the final RF, and I change nothing else, the radio head efficiency is going to go to 25%. Now, if I go back to leaving my final PA stage efficiency to 50%, but I improve my output filter and I improve a little bit my losses in the general and linearization paths, I can still achieve 25%. As I mentioned, jumping from 50 to 60% on amplifier is very difficult. Okay, and going to 70% is even more difficult. If I bring this final PA efficiency stage to 90%, my number here is only going to go to 32.5%. So there's many things my point here is that there's many things that can be done as a system level approach in order to improve the overall radio head efficiency, not just the final stage. You can spend a lot of money and a lot of effort on this number, but it will not yield the best result that you want. That's just the efficiency. That's telling you that efficiency is not everything. In a typical communication system breakdown, the equipment cost is often the biggest concern. This chart might be a slight bit, but I think it's still applicable. The equipment cost is often the biggest concern. We heard yesterday, and of course it's true, that MTBF and ease of installation is important. That's why I'm worried a little bit about radio heads, but radio heads don't have to go at the top of the tower, they can go at the base of the tower. It's still quite a bit of an improvement. Climbing towers, truck rolls for things that break up on the tower is very costly. The operators are very concerned about that, and some of them are very resistant to putting things up on the antenna. Remote maintenance and configuration is very important, and one European operator said upgradability is one of their most important concerns. The system has to be long-lived. So in a typical communication system, whether it's commercial or military, none of these factors change. So as mentioned, efficiency is important, but we need to keep this in mind. Just a quick summary, and I think I'm just about in time. Cost, efficiency, and reliability are key to both commercial and military communication. Widebands, multiple standard operations are driving more challenging designs. Compact size and portability is key, especially in military markets for tactical radios and such equipment. Advanced spectrum techniques will only make matters more difficult. Again, we need more bits per second per hertz. And amplifiers are moving towards the antenna, and I'm sure you're going to hear a lot more of that on the next workshop tomorrow and the day after. Thank you very much.
Thank you, Bill. Questions, please. Yes, sir. Tell us your name and company.
Hi, this is Tim Baum with Richardson Electronics. You mentioned three-way Doherty, and in one of the presentations yesterday, it was pointed out that one of the limitations of Doherty is bandwidth. Is three-way better or worse in bandwidth than standard Doherty?
I think, in my opinion, three-way Doherty is more applicable where you have larger peak-to-average ratios. If you're talking about greater than 8 or 9 or 10, three-way Doherty helps you more. If you're talking about more back-off and keeping your efficiency, I think the circuit will be more sensitive than two-way Doherty. There's novel architectures that have been shown by several manufacturers, but I haven't really seen three-way Dohertys in large volume production. I don't know if anybody else has any experience to see what the yields are. But the yields out there for two-way Dohertys are very good. So there's no question about that.
Does that answer your question? Okay. There was another question in the back? Okay. Go ahead. Florian?
Brent Horine from Hypris. I'm looking for this chart. You just wanted to have one clarification on your chart where you have the 4 different graphs, and that on the y-axis is a correction in dBm.
Right. No, EVM, correction and average power, ACLR1, ACLR2. This chart you're talking about?
Yes.
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 This is ACLR1. This is the DPD correction. This is increasing correction. And this is ACLR2. ACLR2 in this chart is lower the amount of correction because of the noise floor of the measurement system. Okay? So that's all it's showing here.
Okay. And then just a comment that was really brought out yesterday also. I appreciate the overall system efficiency is important, and the power amplifier is not power amplifier efficiency is not the only impact of that, but it still also affects junction temperature and the cost of that element itself and all those type of things.
Yeah, I mean, a typical radio head, I wouldn't say that the transistors are the worst culprit as far as junction temperatures. I think most transistors are designed effectively to be under 150 degrees, and you can even operate much higher than that, in my opinion, with reliability. We've done studies that you can operate at 175, but we don't. No, not many people do. There's other things like the DSP, the FPGAs, other things that are hot that contribute to the overall reliability number. So.
Right, and then there seems to be a trade space between using heftier transistors, more powerful transistors, versus trying to use a more efficient structure that might be more complicated.
Well, I think
It uses more transistors, but perhaps are cheaper. I mean, all the way to an antenna array type system. Can you comment about the trade space, perhaps?
Yeah, as a designer, we always like transistors in a moderate size. I think when you get to very large transistors, you do have effects that come into play that are more difficult. Asymmetrical doherties are becoming more common, so using different size transistors for main and peaking is becoming more common. So yes, you have to play with your architecture both at the system and the circuit level in order to achieve the best results, in my opinion.
Does that answer your question? Okay. Yes, sir. Tell us your name and company, please.
Florian Pivet from Alcatel-Lucent. You mentioned this fact that when you improve the efficiency figure of the transistor device itself, that not necessarily lead to a large improvement of the efficiency of the all-over system. And do the operators that are in the room have any comments on this? Because I think this is a very, very important fact. I think we are spending a lot of money and a huge amount of effort into trying to improve a figure that looks nice on a spreadsheet, but at the end, it doesn't really help the overall system. I don't want to force any operator to make a statement here that we can hold against him, but I would be glad if we could have a talk about this at a later point. So,
well, the operator, in my opinion, the operator cares about everything. As you say, cables, they care about everything, not just the amplifier. Antennas, cables, efficiency, everything.
Yes. Tell us your name and company.
So my name is Hong Wei Kong. I'm from Agent Technologies. So for the APD and the DPD, when you do this kind of comparison, do you do the crest factor reduction first?
Yeah, the signal crest factor was 8 dB for both cases.
Okay.
Yes.
Okay.
Yes. You keep it the same in order to compare the two. But as I said, I think there's room for improvement with both techniques. This is just one of the latest results we have. So.
Okay. Okay. Thanks.
Yes. Steve, tell us your name and company.
Steve Wilkes with Alcatel-Lucent. In the view graph, I think number 5, where you were talking about GaN and how you expect it to grow by 2014, I think you alluded to, but could you expand upon your sense of the robustness and of GaN and its DPD ability?
That was a big question at as I said, the IMS forum that we held. There isn't much data, and I would beg you to ask the manufacturers that are going to speak after me on GaN. I haven't seen a great amount of data. I think some of the effects that we saw early on GaN have been corrected. So there's however, the life tests are not a long way yet to show that it's the same effectiveness as LDMOS. And when it comes to doherties, I think you can make much more effective doherties with GaN, in my opinion, because the transistors are inherently higher bandwidth. You can use them at higher voltage. There's much benefits to GaN. So if the cost of GaN is brought down to a proper level that compares with something like LDMOS, I would naturally choose GaN anytime rather than. But again, LDMOS has a long way to go yet, and still the pricing of LDMOS is unparalleled yet.
Does that answer your question, Steve?
Yes, thank you. But if I can follow up, there's also high voltage LDMOS. Do you have any different story?
There is high voltage LDMOS, but it's not as prevalent as it is it's at low frequencies at VHF and all that. We have high voltage, but at base station frequencies, not prevalent yet. But again, you can ask the Freescales and what the plans are and people are speaking after me.
Okay, Steve, is that all right?
Thank you very much.
You're welcome. Yes, sir. Tell us your name and company, please.
Simon Hamparian with the Andrew Solutions. Just to add to that point, we have done lifetime testing with GaN, accelerated lifetime testing, and we compared with LDMOS, and degradations are very, very similar to LDMOS. Furthermore, we've also done quite a bit of DPD testing with GaN, and they pretty store it, just as well as LDMOS, with much less memory effects.
Correct. Yeah, that's true. It's our experience as well.
Any other questions? I have a question over here. On the chart that showed not necessarily increasing the efficiency of the amplifier, but improving the efficiencies of the other components, one of the factors the operators are concerned about is the costs, the OpEx cost of burning up energy. What I don't understand in your chart is if you don't change the efficiency of the amplifier, how does that impact the OpEx, even if the total system efficiency improves with the improvement of the other component efficiencies?
All I'm trying to illustrate there is that you have to take a system approach. And yes, you have to increase the system of the efficiency of the last stage, but you need to look at other things like the filter, like the linearization losses, and all the other things that go into making a system. So the increasing the efficiency is a must. But all I'm saying is take a system approach, whether it's a radio head or a base station, and reduce the loss in all areas.
Yes, I understand that, but I'm asking the final number in the bottom right-hand corner of that chart you had. When that number increases, does that mean that the power, that the OpEx cost will decrease accordingly? Or
necessarily, yeah, of course.
So that's the power efficiency.
Plus, you can have equipment which doesn't require cooling, as we heard yesterday, natural cooling, all that. Absolutely.
Yes. Okay, thank you. I wanted to understand the chart.
Yes.
Any last questions? Yes, sir. Last question. Tell us your name and company.
My name is Art Earl from Hypers. I just had an administrative question. The market data that you were showing, is that U.S. or global, the ABI research information?
I believe it's global.
Okay, thanks.
Okay. In that case, let's give Bill a great round of applause. Thank you, Bill.